Hello GCSE students. Welcome to this lesson primer for next weekend's lesson. So this is a short video to introduce you to the concepts that will develop more fully in the classroom. Try to put away any distractions and focus, because there will be questions posed today that I'll ask you to answer in the classroom. Okay, let's get cracking. So this is the number tree that we saw last year. And last year we were focusing on primes and composites. So we will review that a little bit. But really we're more interested today in looking at real numbers and how they can be divided into irrational numbers and rational numbers. We want to understand a little bit more about that because it forms quite a big part of the GCSE content. So I'm going to show you this same diagram but in a different way. So in the center of the circle we have the natural numbers, so 1, 2, 3, 4, 5 and 0 there. And then if I've allowed the integers to be included, the negative integers to be included, then that's my full list of integers. If I also include fractions, then that's my rational numbers. And we're looking today out here at these numbers here, which are not rational, so irrational numbers. You can ignore the green bit out here because that's really more A-level content. Okay. So I said we'd review prime numbers. How can you check if a number is prime? Well, a prime number has no factors other than 1 and itself. So to check to see if a number is prime, you've got to check to see if any other numbers go into it. So we need to use these divisibility rules. So you can ask yourself, does 2 go into it? If so, then it's not prime. Does 3 go into it? If so, then it's not prime. Obviously 2 is a prime number. I'm not including 2 and 3 and 5 and 7 when I say this. Does 5 go into it? Now you don't need to check 4, because if 4 is a factor, then automatically 2 must be a factor. So that's why we only need to check the prime numbers that are smaller than the number. And how far do we need to go? Well, as a guide, if you can get a rough idea of what the square root of that number is, that will tell you how far to go. So in this case, 223, well, I know that 15 squared is 225. So I know that 15 squared times 15 is 225. So if I'm going to get two numbers that multiply together to give me 223, and let's say one of them is bigger than 15, then the other would have to be less than 15. Otherwise you'd end up being much bigger than 225 and therefore much bigger than 223. So what that means is, sure, one of the numbers might be bigger than 15, but in that case the other number would have to be smaller than 15. So in this case I only need to go as far as the divisible by 13 rule. I don't need to do the divisibility by 17. Okay, is 2 a factor? Well, no, you can see 2 is not a factor. It's not an even number. Is 3 a factor? You just add up the digits. 2, 2 and 3 gives me 4, 7. No, the sum of digits is not a multiple of 3, so that's not a factor. Is 5 a factor? No, you can tell 5 is not a factor. That's an easy one. Divisibility by 7. Subtract 2 times the units digit from the remaining digits. So what we're going to do is we're going to snap the units digit off of that number. So 2, 2, 3. There, we snap the units digit off. We're then going to double that units digit, so it becomes 6, and we're going to subtract it from the remaining bit of the number that we had left over. So 22 minus 6 is 16. 7, no, 7 doesn't go into 16. 7 goes into 14, but not into 16. So 7 is not a factor. So that's not a factor, that's not a factor, that's not a factor, that's not a factor. Let's try 11. 11 is actually quite a nice, easy one to do. So 11 is just alternating sum of the digits. So what that means is you treat the first digit as positive, the second one as negative, the third as positive, and if there are more digits, negative, positive, like that. So it's positive 2, negative 2, positive 3, negative, and we don't have any more digits, so I can't carry on. Okay. And you just do that sum. So 2 minus 2 is 0, plus 3 is 3, and 11 is 3 is not divisible by 11. So no, 11 is not a factor. And the last one is 13. And the rule for 13 is 4 times the units digit from the remaining digits. Add it. So let's do the same thing as we did before. So 2, snap off the units digit, multiply it by 4, so that becomes 12, and add it on to the remaining digits. So that gives me 34. 13 does not go into 34. It goes into 39, but it doesn't go into 34. So 13 is not a factor. And I told you I don't need to check 17. So I've not found any numbers that go into that. So I'm going to say that's prime. I'm confident that this is prime. What about 9317? Well, the first thing I'm going to tell you is I'm quite scared of this now. I said before we need to go up as far as the square root of that number. Square root of 10,000 would be 100. So I'm guessing we need to go about as far as maybe say 96 or something like that. So now we don't have all of the divisibility rules beyond 17, and you know we don't know the divisibility rule for 89, and we don't know the divisibility rule for 87. So we're not going to be able to do all of the things. So we're not going to be able to see if it's prime. What we are going to be able to do is see if any one of these goes into it. That's the only thing we are going to be able to do. Yeah, it's quite complicated to test if a number is prime. And we're only talking about small numbers. When you get to huge numbers like this one here, then it gets ridiculously hard. Okay, so let's have a go anyway, see how far we get. Okay, is it divisible by 2? Nope, it's not an even number. Let's add up the digits. 12, 13, 20. Nope, it's not divisible by 3. Nope, it's not divisible by... Let's try and see if it's divisible by 7. So 9, 3, 1, snap off the units digit, double it, 14, and subtract it from there. So that gives me 9, 1, 7. Okay, that's still too big for me to check to see if 7 is a factor there. So I'll just repeat the process again. 9, 1, snap off the 7. Whoops. Snap off the 7, double it, and subtract it from there. And so that gives me 77. And 77, I can see that 7 is a factor of 77. And so 7 is a factor of this. So no, it's composite. I was lucky. I didn't need to go beyond, 17. I mean, I got it by 7. I didn't need to go beyond 17. So this is this number here is a famous number because Pierre de Fermat said that he had an equation that produces only prime numbers. It was 2 to the power n plus 1. And if you put in n is 5, you get that number. If you put in n is 5, you get that number. And so what he did was he put it in. Now remember, he didn't have a calculator. So he's a mathematician working in the days before calculators and computers. And so he computed this manually himself. 2 to the power, 2 to the power 5, and then plus 1. And that's that same number that you see here. Okay, and he wanted to check if this number was prime. So what he had to do was lots and lots of calculations to see if this number was prime. And he did it, and he said, I'm pretty sure this is prime. He was confident that this was prime. It turns out, Euler proved this, another famous mathematician, 641 is a factor. It's not prime. So you can see how hard it is to check if a number is prime. In fact, that is the method that computer security is based on. So what a computer does is it takes two large prime numbers and it multiplies those two large prime numbers together to get a huge number. Now, multiplying numbers is easy for a computer. And then it says to the other computer that wants to access the files, do you know what the two factors of this number that I got by multiplying these prime numbers is? Do you know the prime factors of this number? And it's a huge number made of two huge prime numbers. So the computer is going to spend like a day or 2 days trying to find the prime numbers which are a factor of that number. And by then, the other computer says, no, go away. You're not coming into my website or into this because you don't know those two prime numbers. Whereas my computer knows those two prime numbers because it's already passed the security. It's been told those two prime numbers. So my computer knows it. So it's able to access the server. Okay, so a second ago I was saying, how do you do such a big number? And already we've got quite a big number, but this isn't so bad because you can easily write this as two smaller numbers that are multiplied by each other. So you can see the same digits repeated, 150 and then again 150. So you got the same set of digits. And so I'm thinking, well, what if we did 150 times 1,000? That will give us 150,000, but we don't want that. We want these digits to be 150. So we just need to add on another 150. So we times it by 1001. Okay. So those are these are not prime numbers, but these are the factors that make up 150, 150. So now I'm going to do the prime factors of 150. And the way that I'm going to do that is like this. I'm going to do 150 and I'm going to divide it by, let's try the first prime number, 2. So that's going to give me 75. And let's try the next prime number, 3. So that's going to give me 25. And then let's try the next prime number, 5. So that's going to give me 5 and 5. And now I've got to a prime number, I stop. And so the prime factors are 2 times 3 times 5 times 5. So the prime factors are 2 times 3 times 5 squared. That's the prime factors of 150. Now I need to do the prime factors of 1001, so I'm going to do the same thing. Now I want you to do it like this, as long divisions. Well, not long divisions, but upside down divisions, actually. So I want you to do it as upside down divisions, because it's a better method. We'll learn why later on, but it's a better method for doing it. So don't do it as like a spider diagram or whatever other method you might be thinking of using. Don't do it like that. Okay. So I can see that 2 is not a factor. Add up the digits gives me 2. That's not going to work. That's not going to work. Okay, 7. Yes, because if you do the final digit, double it and subtract it from there, you get 98, which is a multiple of 7. So I'm going to divide it by 7. 7s go into 10 once and then carry the 3. 7s go into 30 4 times, that's 28, and so carry the 2. And 7s go into 21 3 times, so 143. Now I'm going to divide that. I can see that 7 isn't a factor of this anymore, but I can see that 11 is a factor, because if you do the alternating sum of the digits 1 minus 4 plus 3, it gives you 0. So that tells you that 11 is a factor. So I'm going to try and divide it by 11. 11's going to 14 once, remainder 3, and 11's going to 33 3 times. And we've got a prime number now, so we can stop. So it's 7 times 11 times 13. So that's 7 times 11 times 13, and then we want to multiply these two numbers together to get this number, and so we multiply them together, and so the prime factors are 2 times 3 times 5 squared times 7 times 11 times 13. So they're the prime factors of 150,150. Okay, we know that from last year. This is also something we know from last year, which is highest common factor and lowest common multiple. So how do I find the highest common factor? Well, I'm going to start by looking at the algebra here. So for the common factors, what you want to look at is something that's in both of them, but if you see the same thing in both of them, so you see the a squared here and you see the a here, so it's the same letter, but this is an a squared and this is an a. You use the one with the lower power. Use the one with the lower power. So the highest common factor is things that are common. the a is common in both of them, but the a squared isn't really common. This one doesn't have an a squared, it has an a. This one has an a, but it also has an a squared, but this one just has an a. So common would be just the a, not the a squared. And if I look at the b's, the b would be common, but not the b cubed. So the b would be common, but not the b cubed. And if I look at the c's, the c would be common, but not the c cubed. So the highest common factor of that is the a, the b, and the c. Is a, b, c is the highest common factor. If I'm doing it for this one, again, I'll start off with the x's. I'm going to use the one with the lower power. The y's, they've got the same power, so I can use either one. I fancy using this one. The z's, the one with the lower power, so this one. And oh, there's a w in this one, but there isn't a w in that one. Well, it's got to be common. So if there isn't a w in the other one, just ignore it. Just ignore the w. And so the highest common factor is going to be, in this case, it's going to be x, y squared, z. Okay, now let's go to some numbers and do the same thing, the highest common factor for these two. Okay, so if we're trying to factorize these, we'd be looking for the highest common factor. And I'm going to do the prime factors again. So I'm going to start off with the 1, 2, 6. I'm going to do the downwards division. That's going to give me 63. 3 goes into that. It's going to be 21. 3 goes into that. It's going to be 7. I've got a prime number, so I'll stop now. So that's 2 times 3 squared times 7. So that's the first number. Let's do the second number. 180. 2 goes into that, 90. 2 goes into that, 45. 3 goes into that, 15. 3 goes into that, 5. We've got down to a prime number. So stop. And so the prime factors of the second number are 2 squared times 3 squared times 5. We were looking for the highest common factor. So we would use the 2, but we wouldn't use the 2 squared. We would use the 3 squared because it's in both of them. We would use the 3 squared. I'm going to use this one. It doesn't matter which one I use. The 5 we wouldn't use because it's not in both of them, and the 7 we wouldn't use it because it's not in both of them. So my highest common factor is 2 times 3 squared, which is 3 squared is 9 times 2 is 18. So 18 is a factor of 126, and it is a factor of 180, and it's the highest number that goes into both of them. Okay, now we're going to do lowest common multiple. And so this time we use the higher power. So if we see the same thing repeated, we use the highest power. So we can see there's an a squared here and there's an a here. So we use the one with the higher power. And then the b, we use the b cubed. That's the one with the higher power. And then the c, we use the c squared. That's the one with the highest power. So the highest common factor, sorry, the lowest common multiple would be a squared, b cubed, c squared. Okay, so for this one, we use the x squared. It's the one with the bigger power. We use the y squared. They're the same, so either one will do. We use the z cubed. It's refusing to highlight, isn't it? The z cubed. And then the w and the x, even if they're not repeated, we still use them. We still use, even if it's not repeated, we use it. So we use the x. It's not repeated, but there is an x, so we want to include it. And there is a w, so we want to include the w. And so the lowest common multiple would be x. There's a w as well. wx. Oh, sorry, x. Oh, hold on. What have I done wrong here? I've done the x. The x I'd already done. It was just the w that I hadn't already done. Let's get rid of that. It's the w that should have been there. Okay, so we're going to use w. We're going to use x squared. We're going to use y squared. And we're going to use z cubed. Okay, so there's our lowest common multiple. So let's go back to these two numbers. We already know that this 126 is... Oh, stop flicking the screen. This 126 is 2 it seems insistent that we must flick the screen. 2 times 3 squared times 7. 2 times 3 squared times 7. And we know that this is 2 squared times 3 squared times 5. And so what we're going to use as our lowest common multiple is we're going to use the 2 squared, the one with the higher power. We're going to use the 3 squared. They've both got the same power, so it doesn't matter which one we use. We're going to use the 5 because we want to include it even though it's not repeated. And we're going to use the 7 because we want to include it even though it's not repeated. So our lowest common multiple is going to be 2 squared times 3 squared times 5 times 7, which is, well, the 2 times the 5 would be 10. I'll do that first. So one of the 2's times the 5 is going to be 10. And then we've got 9 times 7 times 7 times 2 times 10. 9 times 7 is 63. Times 2 is 1260. Times 10 is 1260. So 1260 is the lowest common multiple. So let's say, for instance, I was trying to find the common denominator, and those two were the numbers in the two fractions, then 1260 would be my lowest common multiple. Okay, we're going to do more examples like that in the class, so make sure you know how to do those. Make sure you know the rule for highest common factor and the rule for lowest common multiple. Okay, we're moving on now to look at rational numbers. So rational numbers, if you look at the word, it contains the word ratio in it. So that's a clue as to what rational number means. If I describe your dad as irrational, what would that mean? Now your answer to that might be, well, it would mean my dad's going to come into the classroom and punch you on the nose next week. But that's not what I'm talking about, because that's not what irrational originally meant. Nowadays it's used as a pejorative term. If you describe someone as irrational, they are probably going to get very cross with you, because it's a really insulting word. But that's not what it meant. It meant you can't write it as a ratio, as a rational number. So rational numbers are numbers that you can write as a fraction, and these are numbers that you can't write as a fraction. And so that's what irrational originally meant. Over years, it's changed its meaning in English. It hasn't changed its meaning in math, but it's changed its meaning in English to mean like irrational. You're crazy. You're nuts. You're not logical. That kind of thing. But that's not what it meant originally. So we're using the original meaning of the word, which meant you can't write it as a ratio of two numbers. Okay. So I've shown some fractions between 0 and 1 on this number line. How many more are there that I haven't shown? I'm hoping you know instantly the answer is a huge amount. A fabulously huge amount. An infinite number of fractions haven't been shown. So for instance, if I wanted to show a fraction that exists between a quarter and a third, what I might do, let's find the one that's halfway between a quarter and a third. And to compare them, let's write them as 12s. So let's write the quarter as being 3/12 and the third as being 4/12. And if I wanted something in the middle of them, it would be maybe 3.5 12s, 3.5 over 12. Now obviously that's quite ugly looking, so let's call that 7 over 24. So right in between those is 7 over 24. If I said to you now, find a number that's in between this number and this number, you'd have no problem doing that. You'd say, okay, let's do the same thing. Let's have them having the same denominator so that we can compare them easily. And let's look to see if we can find a number that's halfway in between them. So halfway in between them would be there. A quarter is going to be 6 over 24. And 7 over 24 is the number on the right hand side. And we want halfway in between them is going to be 6.5 over 24, which is going to be 13 out of 48. So 13 out of 48 is going to be slap bang in the middle of those two. And now let's say I want to divide that interval into 2 again. So I want to go into there, in the middle of there. And so that's going to be halfway between 12 over 48 and 13 over 48. And so that's going to be, in between those would be 12 and a half over 48, which would be 25 over, that's 48, over 96. So 25 over 96 would be in between those. And so on. We could do that forever. The denominators will keep getting bigger, but we can keep on going. We can keep putting more and more inside there, more and more and more. We can put an infinite number inside there. And so this is what the Pythagoreans thought. They thought, oh, this is great. You can find as many numbers, as many fractions as you want. The word we use to describe that is we say that they're dense. They're dense. That means that there's a huge number of them. And by a huge number, I mean an infinite number of them. And in between any two, there's an infinite number more in between those. And if you look in between any of those two, there'll be an infinite number in between them. You can keep zooming in and zooming in and zooming in forever, and you'll find more fractions in there. So this was their logic. This is what they thought. They thought, look, you can always find fractions in between any two fractions. And you can find fractions where the decimal is, you know, the decimal representation of it is 100 decimal places, or 500 decimal places, or 1,000 decimal places. There are an infinite number of fractions. Surely any number that you've got, any decimal that you've got, surely we'll be able to find a fraction that represents that number. And that's the logic they use. And that's pretty sound logic to me. That does seem to make sense to me. Fractions are dense. There's a huge number of them. You've got a number. I'll find a fraction that fits it. And the Pythagoreans, they were like a commune of mathematicians. And this is what they believed. They believed that the universe was structured from integers. And they devoutly believed that all numbers can be expressed as ratios. And they call them rational numbers. Ratios. Fractions, what we would call fractions. Fractions and ratios are kind of the same thing. Fraction comes from the word fractio. Fractio means breaking something. So if you break something into two pieces, the ratio will compare the sizes of those two broken parts, and the fraction will compare one part with what it was originally. So they're the same, they're just two different ways of looking at the same thing, ratios and fractions. Okay, so this is what they thought. They thought we'll always be able to write any decimal, we'll be able to write it as a fraction. So let's look at the decimals that relate to each of these fractions. So this one, first thing I'm going to do is I'm going to cancel it down because I can see that 2 goes into the top and the bottom. So I'm going to call that 3421 over 100. And then dividing by 100 is easy. You just move the decimal 2 places. So that's going to be 34.21. Okay? A third, I hope you know that a third is 0.3 recurring. 0.333333333. And they go on and on forever. So the ... is my way of showing they go on forever. But how we write it mathematically is we write it as 0.3 and then with a big dot on the top here to show that 3 is recurring. 15 over 8. So that's 1 7/8. So you can stick that in the calculator, or you might already know that 7/8 is 0.875. So that's 1.875. Okay. I'm not too happy about the way this one's written because you've got decimals inside the fraction. That's not really good form. So I'm going to just double the top and the bottom. So I'm going to times the top by 2. I'm going to times the bottom by 2. And that doesn't change the fraction if you do that to the top and the bottom. So 15 over 27. And then I'm going to divide by 3, top and bottom. So that's going to give me 5 over 9. Now I happen to know 5 over 9 is 0.5 recurring. 0.5 recurring. And we can just stick that in the calculator. 5 over 9 and tell it to decimal it. And it says it's 0.5 recurring. can you see it's put a 6 at the end there? Because it knows that the 5s carry on, and it said, well, the last 2 digits that I can't show you are 5, 5, so I'm going to round off the last digit to a 6 because I'm stopping here. It knows that there's more decimal places than it shows you. That doesn't terminate there, that carries on. It knows that, it can't show you that. 5 divided by 99, let's just decimal that on the calculator. 5 over 99, and let's decimal it. And so that's 0.05050505, like that forever. This string of 2 characters is the repeated string. This string of 2 characters here is the repeated string. And so the way we show that is you write it as 0.05 with a dot on a 0 and the dot on the 5, saying that that's the bit that repeats. From there to there is what repeats. 5 over 999. Decimal that. Okay, so that's 0.005005005. So this time it's a string of 3 characters that's repeating. It's a string of 3 characters that's repeating, the 005, like the 007. And so that's going to give us 0.005 with the digits from the 0 to the 5 being repeated. Let's do 1 over 7. Okay, it doesn't look like it's a recurring decimal, but it is 0.142857, and it's from the 1 to the 7 that's repeating. And I'll show you that. The calculator is sort of said, oh yeah, and then it's 1429, and it's sort of trying to make you think that's not right. I'm just going to subtract that bit from just not the repeating bit, just the 142857 from it, and that will show you minus 0.142857. And this tells you that the calculator knows more decimal places than it's revealing to you. And you can see the rest of the digits are 142857, and so it's got a whole load more digits in there. It's just not revealing them to you. It's being mean. Okay, and then this one again, I'm just going to sling that in the calculator, 2.125 over 0.75, because that's not how I'm happy about that fraction being written. And it says, no, write it as 17 over 6, which is the correct way to write that fraction. And then let's decimal that, 2.83, and it's just the 3 that's recurring. All but 3 of the above fractions are called irreducible ratios or irreducible fractions. So this one here was an irreducible fraction. This one we reduced it, we cancelled it down. This one was an irreducible fraction. This one we had to rewrite it as 5 over 9. This one was an irreducible fraction. This one was an irreducible fraction. This one was an irreducible fraction. Now these are the 3 that weren't irreducible fractions, but hold on a second, I rewrote them. I rewrote that like that. I rewrote that like that. I rewrote that like that. So I turned them into irreducible fractions, you know, because I knew that was the right thing to do. So actually, we ended up with all of them being irreducible fractions. Which are they, and what do you think irreducible means? So, well, irreducible means that you can't cancel the top and bottom down. So you've got an integer on the top, and you've got an integer on the bottom, and there's no, like here, 2 is a common factor. That's no good. Okay. All right. A rational number can be written as a fraction according to these specific rules. A and B are both integers. Yeah, so we had some which weren't integers there. We changed them into integers. B cannot be 0. Yeah, obviously, you can't do 3 divided by 0. That's going to create a mess. And A and B cannot have a factor in common. Yeah, well, we had a factor in common here and we didn't like it, so we cancelled it down. So this is all making sense. You know, write your fraction properly. That's basically what they're saying. Write your fraction properly. Don't be slapdash about it. Terminating decimals. A terminating decimal is one that just stops dead. So this 1.75, it just stops dead. If there were any decimal places after it, somebody has deleted them all and they said, no, I've truncated it, that's my answer, and I'm leaving it at 1.75. I don't care if there were more decimal places, they've gone now. Okay, so this is a terminating decimal. This is a terminating decimal. It hasn't got a decimal point, but you put 0.0 and then it would be a terminating decimal. These zeros here, they're not necessary. So that's a terminating decimal. This looks remarkably like this number here on my calculator. But it isn't. Because this number here on my calculator carries on past here. I mean, the calculator's being sly and not telling you it carries on past here. But if I do, oh, hold on, I need to do answer, subtract 2.7182818. I'll just do that much. You can see there's a whole load more digits. That's the 2 and that's the 8, and that's some more digits there, and it carries on and on and on. So that's that number, but this number does terminate. If I wanted to say it was the same as that number which I showed as being E a second ago, this number here, which is E, then I'd write ... to say, yeah, it carries on, and then that would lead you to suspect it could be E. But this number just does stop here. So that's not E. That's just a terminating decimal. And then this number here isn't a terminating decimal. We know that 0.3 recurring is 0.3333333 ... All terminating decimals are rational numbers. They can be written as fractions. They can be written as irreducible fractions. Okay, so if I want to write this as an irreducible fraction, I'll move the decimal 1, 2, 3 places. So 2, 8, 4, 2. And then if you imagine that as being over 1, and I move the bottom decimal 3 places as well, it'd be over 1,000. Okay. And you can cancel that down. 1,421 over 500. And that's the cancelled down fraction that equates to that. If I stick that in my calculator, 1,421 over 500. The calculator says, no, I can't reduce that anymore. And there's the decimal. So because it's a terminating decimal, we can always write it as a fraction. 5. Just write it as 5 over 1. There we go. That's an irreducible fraction. Okay, this one looks suspiciously like pi, but it's not pi. Here's pi. And if I minus 3.14159265 from there, 9265 from there, you can see there's, oh, hold on, I needed to minus that from there. Let's just do that again, pi minus it. Pi minus that. You can see there's more digits, and there's more. Pi goes on and on. 3.14159265358, blah, blah, blah. It carries on and on, pi does. So this number doesn't carry on, but pi does carry on. This is a terminating decimal. Pi is not a terminating decimal. So I'm going to move the decimal 1, 2, 3, 4, 5, 6, 7, 8 places. So it's going to be 314159265. And then divided by, I moved it 8 places. So 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to divide, 5 goes into the top. So I'm going to divide the top by 5. So that's going to give me 3, 5, 8, 1, 3, 8, 2, 6 divided by, and divide that by 5, so that's just going to be 20,000,000. Okay, so there's my fraction that equates to that and is irreducible. Let's just double check that, see if I made a mistake. 6283185 divided by 20. 1, 2, 3, 1, 2, 3. Okay, so it's 3.1415926.5, and then it's just minus 3.1415926.5 from there, and it's 0 because there are no more decimal places. So that fraction equates to that decimal there. That decimal looks suspiciously like pi. It is not pi. Okay. Recurring decimals carry on forever. So this one is the 4 5s are carrying on forever. We write that as 0.45 with a dot on the 4 and a dot on the 5. That's 0.3 recurring, that's the same 0.3 recurring, that's 0.454545, that's 0.08333333, and that was 1/7. We did that before. All recurring decimals are rational numbers. It's easy to convert any recurring decimal to an irreducible fraction. So here it says convert 0.3 recurring into an irreducible fraction. So that's 0.33. I'm just going to stick it in the I'm going to sling it in the calculator. Now, if I type in 0.3333, it says no, that's not 0.3 recurring. If I type in 0.333, now you can see now mine does terminate, but I've done so many, it's convinced that that's a third. It's convinced that I meant recurring. So it tells me that that's a third. Okay, and I'm going to do 0.45 as well. So 0.4545454545. It's not enough. It's not convinced. 4545. And now it's convinced. Let's just cheat it. Let's do 44, which would not be the same thing anymore. See, it's not actually right. It's actually wrong. But it's approximating and it thinks, look, you probably meant 5 out of 11. Okay. So don't trust the calculator too much. It's a useful tool, but it's also an idiot. Okay, so that's 5 out of 11. Now, what we need to know is we need to know how to do this ourselves, because in the exam, they're either going to give us ones that the calculator can't do, or they're going to ask us to show how we did it. They're going to not accept just an answer from a calculator. So how do we do it? Well, what we do is we multiply it either by 10, or by 100, or by 1,000. It depends on how many digits recur. So what I'm going to start off by doing is saying x equals 0.45454545. That's that number that I want to find. I called it x. Because there's 2 digits in the string that's recurring, because the string that's recurring is just 2 digits long, I'm going to multiply it by 100. And multiplying by 100 is the easiest thing in the world to do. So I'm going to do 100 times x. And that's going to give me 45.45454545. And again, it carries on and on forever. They both do. The 4 5s carry on forever. And now, what I'm going to do is I'm going to subtract them. And that's going to be really nice for this reason here. When I subtract them, 5 subtract 5 is 0. 4 subtracts 0, 0, 0, 0, 0, 0, 0, 0. And I'm just left with 45. And when I subtract them on this side, 100x minus x is 99x is 45. And so x is 45 over 99. I just divided both sides by 99. And we can cancel that down, seeing as 9 goes into that 5 times and 9 goes into that 11 times. And so we get 5 out of 11, which is the same thing. I'm going to give you some of these in the lesson. They'll be more tricky than this one, so make sure you know how to do them. If you need to, just replay it. Okay, so we've looked at terminating decimals and we've looked at recurring decimals. Is there anything left? Well, the Pythagoreans thought not. They thought all the numbers, either what's going to happen is at some point the decimal's going to stop. At some point, even after 100 decimal places, eventually the decimal will stop. And if it doesn't, it might be because it's just the same pattern repeating. And if it seems to be going on, then eventually you'll get a repeating pattern. You will eventually get a repeating pattern, surely. So they thought there was nothing else other than terminating decimals and recurring decimals. And remember that they believed this like a religion. They were a group of people bound together by this idea that the universe was structured from integers, and by dividing those integers you create ratios which they called fractions. Until one of them, Hippasus, was just looking at one of their simplest right-angled triangles, and he was just working out the length of the hypotenuse. So it's got a side here of 1 and another side here of 1, and the hypotenuse is therefore root 2. And he did the decimal for it. He started working out the decimal expansion of root 2. And he worked it out to this many decimal places. And then he said, no, I'll just do some more. It's going to repeat or it's going to terminate. And then he did some more, and he said it's going to repeat. And he didn't have a calculator, so this was hard work. He did more. It's not repeating. There's no pattern that's repeating, and it's not terminating. And he did more, and it's still not repeating, and it's still not terminating. And he's done, like, 30 decimal places. So he thought to himself, what's going on here? So he went to the boss, Mr. Pythagoras himself, the head of the commune, and said, I've done like 25 decimal places. Sounds chuggy, man, but I think it doesn't terminate and it doesn't recur. I'm shook. To which Pythagoras replied, take a seat, bro. I think you've gone delulu. You just got to keep going. At some point, it will terminate or recur. I-wake-a. I don't know if you know what that means. Do you? So that's how they talked in ancient Greek. In ancient Greece, that's how they talked, yeah. He did then start to investigate it some more. And then he came up with a very clever, not even that long, quite short, but very clever way of finding out that this will never recur and it will never terminate. It's a really clever trick. I can't show it to you at GCSE level, but it is something you'll learn at A level. And it's so clever. It's so sneakily clever. And so it's termed an irrational number. Irrational means you cannot write it as a ratio. You cannot write it as a ratio. You cannot write it as a fraction of two integers. And so we call these irrational numbers. Now the irrational numbers, we're going to actually divide them into two groups. So this group here they're not rational numbers. They're real numbers, but they're not rational numbers. But I didn't want to include the 2.25, but it accidentally got thrown into there. These numbers here are called the algebraic irrational numbers, and they're generally square roots and cube roots and fourth roots, things like that. And over here are the transcendental irrational numbers. So out here is a different set of irrational numbers called the transcendental numbers. Now actually you're not going to come across many of those at GCSE, but you have come across one. It's pi. These algebraic ones are called algebraic because they arise when you solve equations. Okay, if you have the equation 2x minus 3 equals 0, so that's a linear equation, it's going to give you a solution which is a fraction. So linear equations, ax plus b equals 0, linear equations are going to give you rational answers. They're always going to give you rational answers, and you can get as many linear equations as you want, and they're going to give you as many rational answers as you want. They'll always be rational linear equations as long as these two coefficients are whole numbers. As long as these two coefficients are whole numbers. I mean, they could be fractions as well themselves. They could be rational themselves, but they can't be surds. They can't be square roots themselves. But when you get onto solving quadratic equations, what happens with some quadratic equations is you get these square roots and cube roots and stuff arising. And so that's why they're called the algebraic line. So the simplest equation I can think of is x squared equals 2. If you solve that, it will give you x is square root of 2 plus or minus square root of 2. And so that's an algebraic irrational number. So these are going to arise when we're solving equations. When we're solving quadratics and cubics and stuff like that, those are going to arise. So they're called irrational numbers. So we're going to come across the ones which are the algebraic ones, and they're going to be termed surds. So they're square roots and cube roots, and they're termed surds. Rather than calling them irrational, algebraic irrational numbers, it seems a bit long-winded, so we just call them surds as an abbreviation. But they must be written in their simplified form. You don't want to decimal them, but you want to write them in their simplest form. So the first rule is the number inside the square root, so this number here should be as small as it can be. And so if you want to reduce that number, what you've got to do is you've got to find a square number that goes into 8. Square numbers are like 1, 4, 9, 16, 20. But obviously we don't want to use 1 because that will be rubbish. So we want to use 4. Well, 4 is good. 4 goes into 8. So we're going to rewrite that as 4 times 2. That's the same as square root of 8, square root of 4 times 2. And then we're going to write it as square root of 4 times square root of 2. And we know square root of 4 is just 2. So we're going to write it as 2 times square root of 2, which is 2 root 2. So that's how that's got to be written. You see how the number inside the surd has gone smaller. Okay, let's do this one. Do 1, 4, not 1, 4, 9, 16, 25, 36. Well, it's only going to be 4 again. So 4 times 3. So that's going to be root of 4 times root of 3. Root of 4 we know is 2. So 2 times root of 3, which is 2 root 3. Again, we've reduced the number inside the square root, so that's considered to be simplified. If you left your answer like this in the exam, you'd lose marks. Okay, because this is a cube root, we're looking for cube numbers that go into 40. So cube numbers are 1, but we wouldn't use 1. And then 8, and then 27, and then 64, and then 125, and then 216, and stuff like that. So 8 goes into that, so we'll use 8. 8 times 5, which is cube root of 8 times cube root of 5. Cube root of 8 we know is 2, so it's 2 cube root of 5. Again, we've made the number inside the square root smaller. Okay, this is rule 2. So your fractions can contain square roots and cube roots, but they mustn't be in the denominator. They must be in the numerator. So what do you do if you've got a square root 2 here in the denominator? Well, what you do is you multiply the top and bottom by that same square root. So you multiply the bottom by root 2 and you multiply the top by root 2. And as long as you do the same to the top and the bottom, you haven't changed the fraction. So that's going to give you root 2 times root 2, which is 2. That's the definition of root 2. Root 2 is the number that multiplies by itself to give you 2. So root 2 times root 2 has to be 2. And then this is 4 times root 2, which is 4 root 2. And now we can cancel down. 2 goes into that, and 2 goes into that. So it gives us 2 root 2 over 1, which is just 2 root 2. Same here. We're going to multiply top and bottom by root 5. So times root 5 and times root 5. And that should get rid of the square root. So on the top we're going to get 2 times root 5. On the bottom we're going to get 5 times root 5 times root 5. Now the root 5 times the root 5 is going to give us 5, but then there's another 5, so that gives us 25. That doesn't cancel down anymore. So that we're just going to leave it like that. It's fine because there's no square root left in the denominator. Okay, this is more tricky. What are we going to do here? Well, what we're going to do is we're going to think about conjugates. So the conjugate of 1 plus x is 1 minus x. They're conjugates of each other. The conjugate of 1 plus root 2 is 1 minus root 2. And the conjugate of 2 minus root 3 is 2 plus root 3. And the conjugate of 5 minus cube root of, no, 5 minus square root of 5 is 5 plus square root of 5. We like multiplying conjugates together. We like multiplying conjugates together. So what we're going to do is we're going to multiply the top and bottom of this by 1 minus root 2 times 1 minus root 2. Why? Because we'll get to multiply 1 plus root 2 by 1 minus root 2, and that's always going to be lovely. You'll see what I mean in a second. So the top is just going to be 1 times 1 plus root 2, times 1 minus root 2, so that's 1 minus root 2. The bottom is going to be 1 plus root 2 times 1 minus root 2, but then we're going to multiply that out. So that's going to give us 1. That's going to give us minus root 2, and this is where it's going to get fun, minus root 2. And then that's going to give us plus root 2, and so they're just going to cancel each other out. They're just going to cancel each other out. And the last one is root 2 times minus root 2 is minus 2. The top we haven't changed, so that gives us 1 minus root 2. So the denominator becomes 1 minus root 2 over 1 minus 2 is minus 1. Now, I want to move the minus up to the top. You can't do that unless everything's in brackets. You can do it once everything's in brackets. So what I'm just going to do is quickly put that in brackets, and then that lets me move that minus up to the top. And now divided by 1, everyone knows you don't need to divide by 1. It doesn't really do anything. And so my answer is minus brackets 1 minus root 2. You might want to multiply that out and call it minus 1 plus root 2 is our final answer. Okay, so that's how we deal with this type of a surd in our denominator. You have to multiply by the conjugate. You have to know what a conjugate is. We're going to encounter more questions like that in the lesson. Okay, rule 3. If you're performing operations on surds, reduce them first. So this one doesn't need to be reduced. This one's fine. But this root 8, we could tidy it up a bit. We could write the 8 as 4 times 2, and then it would be root 8 equals root of 4 times root of 2, which is 2 root 2. So now it's going to be root 2 times 2 root 2. So I didn't change this one, but I changed the other one to 2 root 2. And now when you multiply them together, obviously the root 2 times root 2 gives you 2, but there's another 2 here, so you get 4. So that answer is 4. Root 20 divided by root 5. Tidy up the root 20. It doesn't look attractive like that. The root 5 is fine. You can leave that alone. The root 20, we should rewrite that as root 20 equals root 4 times root 5 is 2 root 5. So that's going to be 2 root 5 over root 5. It's going to cancel out. It's just going to give us 2. Okay, and the last one here, the root 8 we need to fix, but it's going to be the same fix as we did last time. So we're going to, the root 8 is going to be 2 root 2. And then we also need to fix this one, the 1 over root 2. That's going to become, it's going to become 1 over root 2 times by root 2 on the bottom and times by root 2 on the top, which is going to give us root 2 over 2. So that's going to become root 2 over 2. So by the time we've tidied this up, it's going to be 2 root 2, which is the root 8, a quarter plus root 2 over 2. So that was, the root 8 was the 2 root 2, and then this was the 1 over root 2. Let's do common denominator. Let's do common denominator is going to be 4. And so that's going to be 1 plus 2 root 2. And then we'll multiply it by 2 root 2 at the front. We can cancel this down. 2 goes into that once, 2 goes into that twice. And so that gives us root 2, 1 plus 2 root 2 all over 2. We could multiply this out. Root 2 plus, root 2 times root 2 is 2 times 2 is 4, plus 4 all over 2. And we can write that as a half bracket root 2 plus 4 if we want. What I mean by that last stage is this root 2 plus 4 on the top here, the root 2 plus 4, the root 2 plus 4 on the top there. If you want, you can slide it off of the top of the fraction. As long as there's a bracket around it, you can slide it off the top of the fraction. And then there's nothing on the top of my fraction, so just put a 1 on there. And so it just becomes a half root 2 plus 4. Okay. I'm not going to list the homework. I'll give you that in the lesson. What I want you to do instead is focus on the things that I said are going to come up in the lesson and make sure you're well enough prepared for those things. Okay, I'll see you in the lesson. Bye.